you could also send it to other people if you don't want to give the talk again and again. Maybe you will do for your chapter. Okay, good evening, everyone. Welcome to Zurich Earth webinar. And today we have Michael Antonelli speaking with us. So Michael got his higher education in North America, first at University of Alberta, then to University of Maryland, and then got his PhD at UC Berkeley. Before he moved to European continent, first at PGP at France, and currently he's at ETH. So his research interest actually not only involves for the high temperature process, but also including low temperature and surface process, I'd say. So, so today Michael is going to give us example of calcium isotopes to explore the plate tectonic process, I would say. Okay, with that,
a bit of everything.
Michael.
Thank you very much. Thank you for everyone for coming, and Zhengzhu for inviting me. It's a good thing that he asked me to talk about calcium isotopes because that's what I've focused on for the last 6 years or so. So today I'm going to talk to you about calcium isotopes in high temperature processes, so ranging from magmatic systems and some lower continental crust, and then kind of a whole Earth thing at the end. So in general, my work focuses on stable and radiogenic isotope systems, and I explore processes at a wide range of scales, from the quantum level, minerals, rocks, and to the whole Earth. So my past research is focused on magmatic volcanic processes, formation of continental crusts, hydrothermal systems, etc. But I've also done marine geochemistry and some more fun stuff in ecology, biology, and cosmochemistry. But today's talk will be about high temperature systems only. And so here's an overview of today. So calcium isotopes can give insights into processes in a wide range of systems. So today I'm going to share with you some of the problems I've been working on, why these problems are interesting, and what we learned about them using calcium isotopes. I also hope to get across an idea of the kind of fundamental principles that affect all isotopes in general, and how these can be used to gain interesting information on Earth systems. So the first part will be about radioactive element loss from the lower crust. The second part will be about lower crustal processes, so equilibrium versus diffusion. Then we'll look more shallow in the crust, the upper crust, and look at crystal growth rates and timescales in volcanic systems. And finally, we'll end the talk today with going over Archean geodynamics and the important question of when subduction-driven plate tectonics started on Earth. So some of you might be wondering, why study calcium isotopes? Well, there's a lot of them, first of all. There's 6 of them, and they have a very large relative mass difference. So normally we measure 40 and 44. So you got 10%, but you got up to 20% difference if you take into account 48. It's a very abundant element, so it's 5th most abundant in the crust. And on top of all these stable isotopes, it's actually got a partially radiogenic isotopes, 40 calcium, which is the daughter of 40 potassium decay. And another nice thing about calcium is that it's not affected directly by redox effects. And so the processes I'm going to talk about today apply across all isotope systems, but other elements, other isotope systems undergo redox reactions and more complicated things. And so it's a good idea to start with something simpler so you can then start to understand the more complex ones. So there's a relatively large stable isotope, calcium isotope variations in high T systems, up to 8 per mil in metamorphic minerals, 2 per mil in igneous whole rocks. And this is how we define delta 44 calcium. So the same as for other isotope systems, we got 44 over 40 measure. This is in a standard, and there's a lot of different standards for this. -1, and then you multiply by 1,000 to get N per mil notation. So I measure calcium isotopes these days by TIMS, and during my PhD also by TIMS, so double spike for the stable calcium, and unspiked samples for radiogenic calcium analyses. I've also measured calcium by ICP-MS, and this is nice because you can measure a lot of samples at once, but you can't measure 40 calcium. You need a high resolution, additional columns, and then there's some issues with ICP-MS calcium isotope measurements that have recently been kind of brought up in the literature. So it's good to compare your ICP data with TIMS if you can. Typical uncertainties by both methods are about 0.1 per mil. And for epsilon calcium, which is the radiogenic calcium, it's about 1 part per 10,000. There's also some other methods that are promising that are kind of being developed. We have SIMS method for calcium isotopes. These are done in carbonates so far. I think there's one paper on glasses, silicate glasses. Laser ablation ICP-MS, and then of course the new collision cell ICP-MS instruments, which would allow people to measure 40 calcium. It would get rid of the argon interference on that. So other than the high T systems I'm going to talk about today, calcium isotopes are useful in a whole bunch of fields. And so I encourage you, if you're interested, to look at what people are doing with calcium isotopes. It's very interesting. Okay, so we'll move to the lower crust in the first part of the talk. So heat flux estimates suggest that low radiogenic heat production is in the lower crust, so not much heat coming from the lower crust. And there's a long-standing debate about whether this is due to dominantly mafic compositions in the lower crust, or more intermediate rocks in the lower crust, but that have been depleted in the radioactive elements. So here's an example of these two scenarios from Hacker. On the left here, we have a continental crust, which has more mafic rocks on the bottom, intermediate in the middle, and more felsic on top. And then here we get basically the same heat flow, but we have a lower crust and middle crust that's intermediate rocks, but these have lower radiogenic element abundances, so uranium and potassium. So lead isotopes suggest that there's loss of uranium from lower crustal rocks, but potassium isotopes are poorly constrained. They're mostly gotten at by losses in rubidium. So you look at the rubidium-strontium ratio, rubidium isotopes, and you say potassium must have done the same thing. Importantly, 40 potassium was the largest source of radioactive heat on the early Earth. So until about 3 billion years ago, potassium was gave more heat than uranium or thorium. So here's what the decay looks like. You have 40 potassium decaying to argon, which everyone knows about from potassium-argon dating. And so that's about 10% of the decays, but 90% of these decays go to 40 calcium. And unlike 40 argon, 40 calcium is not lost through, easily lost through high temperature processes, like a noble gas is. So you can use 40 calcium to try and constrain potassium losses from the lower crust. So in this study, I analyzed radiogenic calcium abundances in lower crustal granulite minerals from 3 different locations. So Antarctica, Canada, and in Italy. And garnet is very nice in terms of all these minerals. Garnet is very nice because it excludes potassium very effectively. So you have zero potassium. So what you get in the garnet, if there's any radiogenic calcium in the garnet, it has to be inherited from earlier potassium decay in the protolith rocks. So these are the results. On the y-axis, we have radiogenic calcium abundance in garnet. And on the x-axis, we have garnet grossular content, so the amount of calcium end member in the garnet. And you can see here that we get very large enrichments in the garnet, even though there's no potassium, up to about 42 epsilon units here. And these are higher in the politic samples than in the mafic samples. So garnet epsilon calcium depends on potassium calcium ratio in the protolith rocks and the time difference between the formation of the protolith rock and the metamorphic ages, so the formation of the garnet. And for all these locations, we have available age estimates for crystallization from uranium lead dating. And we also have protolith age estimates from neodymium and other systems. So for a given metamorphic age, younger protolith ages require higher potassium calcium to reach the same initial epsilon calcium value. So if you have younger ages, you need even higher potassium calcium to get that radiogenic calcium ingrowth before the garnet forms. So what we did is we used the oldest protolith age estimates from each location, and this gives you a minimum, potassium calcium in the protoliths. Then all you have to do is compare that to the potassium calcium ratio measured in the rocks today, and you get this figure here. So on the y-axis, we have potassium over calcium that you measure in the rocks today. And on the x-axis, we have the potassium calcium estimate for the protolith. And you can see that basically all of these samples here indicate significant amounts of potassium loss. So it looks like most lower crustal rocks have lost more than 2/3 of their initial potassium, and that's due to lower crustal metamorphism. This suggests that crustal heat flow estimates are consistent with radioactive element depleted intermediate rocks as opposed to just mafic rocks in the lower crusts. And this has significant implications for coupling between crust and mantle in the Archean, so cratonization. So before we move on to the next part of the talk, I just wanted to take a quick detour and talk about the 40 calcium over 44 calcium of bulk silicate earth and seawater. So this is from a recent paper we put out last year. And so here we're looking at the absolute 40 calcium over 44 of SRM 915A. And this is a compilation of the average value from different studies. So here we have 15 different studies, the average value from each one. And these get down to very low values, and that's because different machines give you a different absolute ratio because it's not relative to anything. So if you exclude a few outliers, you get this better constraint near about here. So what we did in this paper is we measured mantle, so basalts, oceanic basalts, and seawater and rivers. And you can basically see that there's this about 1 epsilon unit enrichment in seawater relative to mantle. And this is actually true for SRM 915A as well. And we actually measured strontium isotopes in SRM 915A just to kind of, we were wondering whether that standard comes from seawater calcium in the first place. It's very hard to find any information on it. So we measure 8786 strontium, and we also get a seawater value, just like we do for epsilon calcium. So long story short, we recommend a value absolute 40 over 44 value of 47.1622 for 915A and 47.157 for bulk silicate earth. And then we actually use this in this paper. It's not really relevant to the topic today, but we used it to get at the relative calcium fluxes from different reservoirs. And the big conclusion of this paper is that these diffuse low temperature alteration of mid-ocean, of just oceanic crusts, does not contribute as much calcium as rivers and groundwater, only 10 to 40% when combined with the high temperature fluids. So that was the big conclusion of this paper. Okay, now we'll go back to the lower crust. So the next step in the lower crust research was to analyze the stable calcium isotopes in the granulite separates. And so we expected that we would find isotopic equilibrium between the different minerals because they're heated for tens of millions of years in the Napier complex in Antarctica up to 100 million years at high temperatures. And there's major element equilibrium. So when you measure the major elements by microprobe and you put it into a program like TweakQ, you basically get equilibrium. So the initial goals of this were to establish delta 44 calcium as a geothermometer for metamorphic rocks. and to understand mineral fractionation effects in igneous rocks, where delta 44 calcium variations are very often linked to source variations, such as carbonate recycling in the mantle. And that's very common. And this is why people do that. So here is a figure from Liu and Lee, 2019. You can see a histogram here of the delta 44 in carbonates compared to in peridotite samples. And you can see it's more negative. And so since about 2011, people have been using this observation. And when they see these negative trends in igneous rocks, here we're looking at Hawaii, they like to ascribe this to carbonate assimilation. So though typically assumes that high temperatures equal equilibrium for isotopes, we had no idea what to expect in terms of the magnitudes and directions of intermineral fractionation. This was in 2019 or 2018. And so equilibrium delta 44 calcium values depend on the CaO bond strengths. And these can be estimated from quantum mechanical simulations, so ab initio calculations. So I enlisted the help of Edwin Schaubel at UCLA to do a bunch of these calculations for us. And so here on the y-axis, we're looking at the reduced partition function ratio, and on the x-axis, the temperature. So basically the y of high delta 44, low delta 44. And you get this general trend where olivine is the heaviest, garnet, OPX, CPX, hornblende is empirical, apatite, empirical melt, plagioclase. And so at 900 C, which is the temperature of UHT metamorphism in a lot of our samples here, we'd expect a range of about 0.8 per mil if everything was at equilibrium. So now that we have some idea of what to expect, how does this actually compare to the mineral separates from our 3 granulite facies localities? Well, here's a graph of delta 44 calcium corrected for radiogenic ingrowth. And we can see that these minerals have a range of about 8 per mil. So these delta 44 variations are an order of magnitude larger than predicted at equilibrium. And this was very unexpected given the long time scales for equilibration and that you get major elements equilibrium. Another puzzling observation was that it seemed like this equilibrium was increasing with temperature. So here we have 2 graphs here. On the left panel, we have the magnesium number in garnets, and then capital delta 44 calcium on the x-axis. So that's the difference in this panel between garnets and other minerals, so feldspar, CPX, OPX, whole rock. And here on the right, we have the modal OPX content of the samples versus the same thing. And here all the OPX versus other mineral values. And both of these y-axes are typically associated with increasing temperatures. So it seems like, oh, and I forgot to mention these vertical bars here, color, those are the predictions for the various mineral-mineral equilibrium at 800 C. And at higher temperatures, they collapse down to 0. So it seems like high temperatures do not actually equal isotopic equilibrium. These fractionations are likely the result of kinetic effects during metamorphism. But of course you can ask, are the ab initio estimates actually reliable? So what we did is we leveraged triple isotope analyses, which are typically used for cosmochemistry. That's where you measure more than one isotope accurately and precisely. And you can use this to distinguish between equilibrium and kinetic fractionations. So the different relationship between 42/44 and 48/44 calcium basically is the relationship is different for diffusive kinetic fractionation and equilibrium. So there's 2 main types of kinetic effects. The first on the left here is what we call diffusive kinetic fractionation. So this is from translation or diffusion through a medium here. And so lighter isotopes go faster and heavier isotopes go slower. And that's just due to 1/2 mv squared, the kinetic energy, right? And then we have reactive kinetic fractionation. And so that's based on vibrational frequencies, quantum mechanics. And so when you get equilibrium, you have equilibrium between the reactants over here and the products, and that gives you equilibrium fractionation. But when you have reactive kinetic effects, what you're getting is equilibrium between reactants and a transition state. And the transition state is typically loosely bound, it's weakly bound. And so what you get is a light isotope enrichment in the transition state, and then that drips over to the product side here. So the important thing to get from this is that because these are vibrational, they give you an equilibrium mass law based essentially on Hooke's law for a spring. And these, because they come from kinetic energy differences, basically give you the diffusive mass law, which is in an ideal gas. This is Graham's law. So we define a new variable, this capital delta 48 calcium prime. And this quantifies the deviation in measured delta 48 calcium from an equilibrium mass law. So that looks like this. We have a cap 48 calcium, which I'll call it. It's equal to the 48 over 44 calcium that you measure minus the 48 over 44 that you expect at equilibrium. And that is equal to the 42 over 44 calcium that you measure to the power of minus 1.751, which is the equilibrium mass law over here. So we decided to test this prediction by measuring two end-member samples. And this was done by multi-collector ICP-MS in Copenhagen by Martin Schiller. And basically we analyzed OPX and plagioclase from slow-cooled gabbro. These minerals agree with ab initio predictions at the right temperature. And then we measured plagioclase in glass from rapid crystallization experiments that we did at ETH, where there's an over 2 per mil difference between the plage and the glass. And I'll get back to that later in the talk. So here we're looking at a graph of Y is the delta 48 calcium. And on the x-axis, we have delta 44 up here, 42 or 44 down here. So the first thing to notice is that the sample still water here has no delta 48 calcium difference between the OPX and the plagioclase. And when we look at the experimental plagioclase rapid crystallization, we can see that it agrees very well with the diffusive kinetic mass law, surprisingly well, especially because this is an ideal gas. The mass law comes from an ideal gas. So that was quite surprising that it fits so nicely. So then we look at other plutonic minerals. These are from a lower-crustal garnet-bearing gabbro from Ivrea. Those also have no delta 48 calcium difference. And then we looked at the center and the edge of a mafic dike that was metamorphosed from the Napier complex, and that also agrees very well with the diffusive kinetic mass law, even though these are whole rocks. And then when we look at our granulite minerals, we see that they don't agree as well with the diffusive kinetic fractionation, but there's definitely a diffusive component. These agree pretty well, and this one might have been offset by later trying to reach equilibrium again after the diffusion. So great, we've confirmed that we're getting kinetic effects, big kinetic effects from diffusion in granulite facies minerals, but that's great, but what information can be gained from these diffusive effects other than just saying we don't have equilibrium? Well, we thought we could address this classic debate in metamorphic petrology. And that is about how does the lower continental crust lose its incompatible elements? So I showed you earlier that potassium is lost. Thorium people are unsure about, but uranium is lost from the lower crust. And so this could occur either to partial melting and then loss of that melt. And then other people think that it's just dehydration. And then you lose the fluids that are enriched in these incompatible elements. So we can use the diffusive kinetic fractionations to model calcium transport. And so this is a photo of the last samples I showed you on the delta 48 calcium plot. We have the center and edge of a mafic dike surrounded by a quartzitic country rock, sorry. And then we use these the calcium isotope values, center and edge, as inputs for our numerical diffusion. And so here we're looking at the change in calcium isotope composition from initial, and here distance. And so in the middle, we have the ultramafic dike intruded into the country rock, and then it's all metamorphosed at high temperatures for a very long time. And as that happens, basically the light isotopes of calcium move faster away from this dike. And so you get this negative pulse in the country rock. The important thing to note is at the beginning, you get this shape that you see here, so two horns, and the middle is still at the zero value. So we can constrain that very well, and we have the concentrations as well. And we have time estimates, 100 million years. And so we can get at the diffusivities and the isotopic diffusivity ratio, so the diffusivity of 44 calcium over 40 calcium. And these basically suggest that grain boundary diffusion is occurring through a melt of dacitic composition. So when you look at that, that indicates that incompatible element losses during granulate species metamorphism are from partial melting and not dehydration. So you can rule out just dehydration. Now we'll look at the lower crustal minerals. So given that we have these diffusive effects in the minerals, it seems that disequilibrium in these mineral grains are also from calcium diffusion, probably from transport of calcium towards the growing garnet grains or whatever it will be. And what we found is the minerals with largest disequilibrium delta 44 calcium are from locations with counterclockwise PTT paths. So basically isobaric cooling from ultra high temperatures. And so this is speculative for now, but basically we imagine that, so if you have a clockwise path in PT space shown in green here, you have your garnets, everything's okay, just cool down. But if you're over here, so very high temperatures, and you cool isobarically, then your calcium is coming from plagioclase and these other minerals, and it's diffusively fractionated during formation of the garnet. So that's the working hypothesis for now. So the summary of the lower crustal results, basically high temperatures do not equal isotopic equilibrium. We find large delta 44 calcium variations in whole rocks and minerals, and we find that they're mostly diffusive kinetic effects causing these. We can use triple calcium isotope analyses to distinguish between equilibrium and diffusive fractionations. And finally, incompatible element losses from the lower crust are likely caused by partial melting. Okay. Now we'll move on, we'll move upward in the crust to the upper crust. And we're going to look at phenocryst growth rates and volcanic timescales. So the growth rate of phenocryst is intimately linked to volcanic recharge and eruption timescales. And it's necessary to understand these, to understand the tempo of volcanic systems. So there's some other methods to get at volcanic timescales. One of those is absolute age dating of the crystals. So you measure a zircon age and you say, well, the magma must have been active for this long. People do trace element diffusion profiles across crystals. So these assume that the crystals grew instantaneously with a flat trace element profile, and then these diffuse out over time. And you can basically get at time constraints if you know the diffusivity of your trace elements. And people do this with phenocryst crystal size distribution analyses. And so when you plot the size distribution of crystals, the slopes are proportional to the growth rate, 1 over the growth rate times the growth duration, so this time. So when you use these methods, there's an apparent increase in volcanic timescales from mafic to silicic systems. So we have an opportunity to test this hypothesis by using our diffusive kinetic effects to constrain crystal growth rates. So the model for that looks like this. You have a growing crystal and diffusion through a boundary layer where you can get diffusive isotope fractionation during crystal growth. So when an element, when the isotopes are being transported towards or away from a growing crystal, they can undergo kinetic fractionations through the boundary layer. So here's just some examples of what boundary layers can look like. Here we have magnesium map around a speletal olivine grain. So you can see that magnesium is depleted around the growing crystal. And here we have a boundary layer around a growing plagioclase, which is iron rich, but also calcium poor. So here's that model again. And basically the way this works is, so if the element, in this case calcium, is compatible in the crystal you're growing, your diffusive boundary layer is going to get depleted in calcium. And then through that, from the bulk magma, the 40 calcium will diffuse faster than the 44, and you'll get this inherited kinetic effect in the growing crystal. And the opposite is true if you have calcium is very incompatible in a mineral. And this will cause calcium to build up in the boundary layer. And then as it diffuses away, the 40 calcium diffuses away faster. And you get this positive kinetic offset in your calcium isotopes. And just to note, this is true for every isotope system. And involved in a project now looking at zirconium isotopes and zircon with some colleagues in China. So the original prediction for these effects comes from Watson and Mueller, 2009. And they predict that you get increased disequilibrium with increasing growth rates relative to diffusivity of the elements, in this case calcium, in the melt. And that's the big difference compared to the diffusion profiles in grains, is that those rely on diffusivity in the crystals, but everything is happening in the melt. But this has never been experimentally verified, and it hasn't been applied to natural systems. So we started with plagioclase growth experiments, basically rapid crystallization of plagioclase from haplotonolithic melts. And we did this with 3 different water contents and the same cooling rates. And so we found very large calcium isotope effects over 2 per mil. So this is the same, this data point right here is the same I showed in the CAP48 calcium plot. So here we have the difference in calcium isotopes between plagioclase and glass. And here on the x-axis, we have the amount of H2O plus CO2. And you can see that the drier the sample is, the less kinetic fractionation you get. And this makes sense because higher H2O increases the calcium diffusivity. And so that decreases your growth rate over diffusivity value. And we know that diffusion is happening in these because, as I showed you earlier, we have the delta 48 calcium measurements. So all this together confirms the theoretical predictions from Watson and Mueller. So now after that, we decided to look at natural samples, and we looked at some young phenocrystic volcanics and magmatic orbicules and comb layers from California. And so for the phenocrystic samples, here we have a plot on the y-axis, delta 44 calcium difference between the mineral and the matrix. And here we have basically the distribution coefficient for calcium mineral matrix. And so the observation from here is that plagioclase is always lighter than matrix, so always lighter than melt. And CPX and hornblende are always heavier. When we look at the orbicules and comb layers, just plagioclase separates, we get this observation here, basically that the matrix cores and the host rocks of these orbicular diorites have heavier calcium isotopes than the combs and the rims. So this suggests that the combs and rims grew faster. So we put that into the model and make a few assumptions about boundary layers and diffusivity of calcium, and we get these results here. And basically what we see is that calcium isotopes suggest rapid growth rates, especially in comb layers and orbicules, and in some phenocrysts, up to about 25 centimeters per year. So quite fast. And basically we can take these growth rates and combine them with the crystal size distribution analyses to get at crystal growth timescales without having to assume the growth rates like people do when they usually do CSD analyses. So here's the results of that. We have a modified figure from Cooper et al. Paper. And this is from the PNAS 2019 paper. And basically in orange here, we have timescales estimated from diffusion profiles of trace elements and phenocrysts. In blue, we have calcium isotopes. And you can see these are sorted from mafic to silicic. And you can see that mafic samples before, there was this kind of nice trend between mafic to silicic, where timescales get longer in silicic systems. When we look at the calcium isotopes, we see a very different picture. We see that both silicic and mafic systems, crystal growth rates were similar, the growth durations were similar. And much shorter than you get from these other timing constraints. So calcium isotopes plus CSD indicate short crystal growth timescales for both mafic and silicic systems, and that in turn suggests that they have similar recharge and eruption timescales. So this work could be continued using any isotope system you want, as long as it diffusively fractionates in a melt. So to continue that work, I'm currently working on developing SIMS analyses and plagioclase. This has been hindered by COVID, of course, but it's kind of what I was supposed to be doing here during my postdoc at ETH. And so this would be very nice to develop because the smallest crystals are most likely linked to the fastest growth rates and the eruption timescales. So I'm working on these with Anne-Sophie Bouvier and Anders McCarthy, so University of Lausanne and ETH. And if we can get this to work, it's going to be very nice for understanding diffusion timescales, transport, mineral formation in magmatic systems, but also in metamorphic rocks, and understanding how these rate-dependent fractionation effects vary in individual crystals. So that'd be great. Okay, I'll get to the final part of the talk now. I'm just checking my time, it seems okay. So we'll get to the final question of when did plate tectonics start on Earth? And this is obviously, you guys know that there's an ongoing debate about when subduction started. And that's because this is a very important question to understand. It's fundamental to Earth's evolution. And previous estimates range from Neoproterozoic, if you look at the appearance of paired metamorphic belts, to Eo-Archean, if you look at various isotope systems and other constraints. So the oldest rocks in the world are known as TTG suites, tonalite, trondhjemite, granite diorites. These are Archean granitoids, and they're up to about 4 billion years old. So here's just a picture of what they look like. Here we have some TTG dikes. This is from the Nulu-Agatuk supercrustal belts hosted in amphibolites here. So these are the dominant rock type in the Archean. And one thing we know about the Archean is that there was much higher mantle temperatures. So maybe there's a link between these things. So we're wondering, what can calcium isotopes tell us about the way that these rocks formed? And can we identify recycled carbonate sediments in their sources? If we could, that would indicate subduction. But before we can get at any kind of source variations, because of what I've talked to you about earlier today, we need to account for magmatic effects. So unlike granulites and the volcanic systems I discussed earlier, the plutonic rocks I've shown you a few data from in the delta 48 calcium plots appear to be at equilibrium, the minerals in those samples, and they agree with ab initio estimates. So our approach here was to use ab initio delta 44 calcium predictions and pair these with phase equilibrium models for TTG petrogenesis to get at model melt compositions. So we modeled mineralogical changes during partial melting of hydrated basalts along 3 different geothermal gradients. So here we have a 500 degrees C per GPa gradient. So this is the coldest we do, and 1000 degrees C per GPa over here. You can see the biggest difference between these is the amount of garnet in your residual minerals. So on the top here, we have weight percent of each mineral. And on the bottom here, we have the amount of calcium that each mineral is contributing. So you can see at these low geothermal gradients, garnet takes the lion's share of the calcium. And then we modeled the composition of these liquids, and those are the TTG melts. So we take these ab initio estimates where the minerals have this order, and we take into account the changing residual mineral proportions along these paths here, the compositions, so the amount of calcium obviously changes at each temperature in each mineral, and obviously the fractionations are also affected by temperature. So you take all of these things, account for all of those, and you get this figure here. So we have the delta 44 calcium, bulk silicate earth, on the y-axis, and the temperature here. And basically you can see that because garnet is one of the heaviest calcium bearing minerals, the low temperature path, the low PT path has the largest fractionations, so largest negative fractionations. And we also did these dotted lines here, which are garnet fractionation scenarios where garnet is removed from the system every time it reaches about 5 weight percent. So you can see that we can get these quite large variations in delta 44. So then we measure the delta 44 in a bunch of carefully selected TTG whole rock samples. They were selected for minimal alteration, and these range in age between 4 and 2.8 billion years ago. And we compare these to our model results. So here we're looking at a graph of delta 44 on the y-axis and dysprosium over ytterbium on the x-axis, which is a proxy for increasing residual garnet in the rest type. And what you can see here is that most TTG samples are consistent with our 500 degrees C per GPa models. And that is the same as you get in modern hot subduction zones. We have a few samples that don't agree with the models. These have positive europium anomalies and negative europium anomalies, so they're likely from plagioclase accumulation and fractionation, and that makes sense with our DFT predictions. But the Nuvu-Agatuk samples, so those TTGs I showed you a picture of, can't be explained by our models. They're much more negative. And these are very special rocks. They're allegedly some of the oldest on Earth, so people looking at 142 neodymium constraints have claimed that they are 4.2. And they're one of the few Archean rock packages that exists that can actually tell us about early Earth geodynamics. These samples are also special here because they have very high paraluminosity. So this is aluminum or calcium, sodium, potassium, molar. And basically we have increasing paraluminosity. So these are likely to be incorporating sediment assimilation. So to get these high aluminum values, they have to be politic sediments. So although the effects we're seeing, these negative values, could easily be kinetic effects based on everything I've told you, we have other evidence for sediments in these samples. So some of that is that they have high 18O values, plus 10, I think 9.5 and 11 in the two samples. And there's this other evidence for sediments in the Nuvu-Agatuk TTGs. There's high 30 silicon, delta 30 silicon, and this has been interpreted as oceanic chert incorporation into the TTG precursors. We have high 57 iron values. This has been interpreted as carbonate incorporation. And of course, metapelites are common in the area based on studies of the amphibolites here. So this suggests that there can be 3 different types of sediments incorporated into the protoliths for the TTGs, or incorporated after they melted. And these are often found together in accretionary prisms, so it's not that crazy. So the low delta 44 we get in those samples is probably from incorporation of low delta 44 high calcium concentration sediments. So most likely carbonates. But how do you get such low delta 44 calcium in carbonates? The average carbonate value is minus 0.35 in the Phanerozoic compared to bulk silicate earth. And if you look at even older carbonates, they're basically the same value as bulk silicate earth. And so one of the ideas that we put forward in this paper is that one way you can get such low values is that you have mantle buffered Archean, Archean seawater. So the Earth was hotter, you have much more hydrothermal circulation, and this keeps the Archean seawater at a value of 0, which is, or essentially 0, which is the same as bulk silicate Earth. And then if you precipitate a carbonate with the same average fractionation you get today, you can get down to about minus 1.25 per mil. And this is similar to what's inferred for 8786 strontium. As you go back in time, seawater values for 8786 get closer and closer to mantle values. So we did some simple mixing models here to estimate the amount of sediments that it would take to do this. And so these are 3 end-member mixing models. And the end members are shale, these hypothesized Archean carbonates, and the average TTG. So here we have A over C and K on the y-axis of paraluminosity and 18O on the x-axis. Here are our 2 Nouveau-Agatuk samples. You see they fit pretty nicely between average shale and average TTG. And so if you add carbonates to it, you swing this way. And then here we have delta 44 calcium versus delta 18O. And you can see that the TTGs fall nicely along this mixing trend between the 3. And basically they indicate that you need 30 to 50 weight % sediment assimilation. So that's total sediments. And that in those sediments, 5 to 20% of those sediments were carbonates. So this is a little high, but it's not higher than other estimates for other types of granitoids. So along with our geothermal gradient estimates, which are the same as in modern Haas subduction zones, so where you get modern anakites, for example, these are the geothermal gradients. This carbonate signal suggests that subduction started early and occurred repeatedly throughout the Archean. So this is just kind of a picture of what the Archean Earth could have looked like, much like today, except you have this mantle buffered basaltic oceanic, basaltic composition, mantle composition, seawater. And then you can incorporate the cherts and the carbonates and the mudstones along with your subducting package. So with that, I'd like to acknowledge all of my co-authors on most of these papers here. So these have all been really great people to work with, and especially my advisor, Don, Paulo, and my master's advisor, James Farquhar, who have always been really helpful. And that is it. And here's just some screenshots of the different papers I talked about today for future reference. So with that, I'll take any questions you have.
Okay, thank you very much, Michael, for your talk. And now questions from our participants. So feel free to open your mic, ask a question, or raise your hand, or you can leave your question in the chat, and I could read the question for you.
Should I read this, or you got it? Thanks.
Okay, let me read it. It looks better. Okay, so his question for Archaean from IIT India. Apart from the carbonate contribution for different types of granitoid sources, Si or A type granites, can the source assimilation related isotopic fractionation effects due to sedimentary paletic and the mantle contributions to be quantified with much precision?
I mean, what I get from that question is basically asking if S-type granites and things can be distinguished, or sedimentary versus mantle. Is that the question? It was a bit long, and I.
Yeah, I think it's a better question. Well, or you can open your mic.
Am I audible?
Yes.
Yeah.
Yeah, my question is like for different types of granitoid sources, as well as like the processes which might relate, which might be related to the assimilation and fractional crystallization processes at the subduction zones. So like, can it be constrained with much precision? The different types of 40 potassium volatile related recycling of the crusts for different
Right.
subduction.
Okay, I think I get the question. So you're asking basically if we can basically get at the source variations for sediments, mantle contributions, etc., after correcting for partial melting, fractional crystallization, stuff like that. If that's a question, I would say not that well. Basically, what we have to do is correct for all the possible processes that could happen on the way to your granite. And then maybe from that, you can get at the source variation, but it's much easier to do with a radiogenic isotope system because these calcium isotope variations are huge from fractional crystallization and other things. I'm actually working right now on, I'm almost done a manuscript on modeling granite petrogenesis with calcium isotopes. So hopefully that comes out soon.
Next question, please.
Hello, I have a question to Michael. Yeah, first, thank you very much for your nice talk. And I have a question regarding to the radiogenic calcium isotope for granular studies. Yeah, based on your information, it seems the residues, for example, granular residues experience melt loss, and the calcium 40 still can record as a protease, which is rich in potassium or not.
Yeah, that's the beauty of it.
And the start when, like, it must be this sample has been in a key order, or if later, for example, the granular process happened, for example, proterozoic will not be so effective compared to Archaean samples. Or
Yes. No, exactly. You got it. The youngest sample we did with these methods were from Ivrea, and those are 400 million years old. And those are basically at the limits of our resolution. We were able to get still a nice isochron, about 0.4 plus or minus 0.2 billion years. And so that's, yeah, you're right. It's basically most useful for old rocks because as you saw in that that figure of the concentrations of these elements through time,
I think
how is it?
Maybe the 7th slide.
Yeah. So the 40 potassium is very low today. And so you don't get much variations as much as you used to. Yeah.
But if, for example, the metamorphism is around 3 billion years, it will be fairly effective for recorded, right? Because I have, which now they are very high temperature granulates, which is the experiences peak metamorphism around 1100 degrees C, and these samples are highly depleted. But
wow, those are hot granulates.
yeah, correct. And the protease we postulated they are the metapelites and also fairly potassium rich. Yeah, but currently we have found no potassium phase in this rock. They must experience a high.
So they lost. So you think they lost all their potassium? That's quite possible. We have one sample like this right here, which seems to have lost 99.9% of its potassium. There's basically zero in the rock today. So those sound like very interesting samples. And if there's garnet in there, it would be very interesting to measure radiogenic calcium.
Yeah, that's what I'm interested. Yeah, they're very garnet rich. They're practically more than 60% or 70% are only garnet, and the rest plagiaries and also sillimanites. So that's why I'm quite interested if these samples can be measured with the radiogenic potassium. And
I would be very happy to look at those if you wanted to send them. But
of course, but the problem is that the sample is relatively small. So this leading to my next question: how many samples will be required for such analysis?
You only need 30 micrograms of calcium, and you could do less than that, but that is ideal. then I can repeat the measurements 7 or 8 times if needed. But we can go down to 10 micrograms. And so it depends on the amount of calcium in your garnets, but not that much. I would say less than 10 milligrams usually.
Yeah, so should be sufficient. Yeah, that's definitely more than, yeah, I can easily reach 100 milligram or 200. Wow, that was, so probably, yeah, I can contact you by email. Yeah.
Please do, that would be great.
Yeah.
I'd be excited to look at granulites again because I haven't in a little while.
Yeah, and this granulite I got as a garnet uranium age is around 3.1 ppm. So they are definitely perfect for such progress.
Okay, and there's
Yeah.
protolith age estimates too, or
Sorry?
are there protolith age estimates?
Oh, the protolith is definitely much older. So based on the inherited silicons, should be around 3.4, yeah, billion years. Yeah.
Okay.
So the
Yeah,
metamorphosis.
send me an email and we can talk more about it if you'd like.
Yeah, of course. Yeah, we'll be very happy to talk to you later. Yeah, thank you.
Great, thanks.
Next question, please.
I see a question in the chat. Should I read it?
Okay,
I see
I
two
can
questions.
read it. So it's a question about TTG. So should we worry about that long-term weathering have influenced the TTG's calcium isotopes?
The short answer is probably, but the samples that we chose. So in that study, Martin Guitreau had all the samples, and he chose 19 TTG samples from about 150, and they were the least altered. They have the same epsilon hafnium in the zircons in the whole rock, and as far as TTGs go, they were quite fresh. So not that fresh, obviously, after 4 billion years, but much better than all the other TTGs in his collection. So we don't think it was any kind of weathering that affected the calcium isotopes.
Okay, I think we'll wrap about 60 minutes and 59 minutes. That's okay. Okay, thanks again, Michael, for your talk, and thanks everyone for your participation. So next week, Mingmen Li from Arizona State University are going to talk about large low shear velocity provinces at the webinar next Wednesday. So have a good day or have a good evening, everyone. Thanks again, Michael, for your talk.
Thank you very much for the invitation. Thanks, everyone.